Hi friends, now we will start discussion on the topic heavy crude oil processing. As we have discussed in the previous classes that cleaner production of liquid fuels from petroleum crude is possible by implementing the practice to remove the impurities from it and then upgrading the vacuum residue, and another was to develop technology for the treatment or for the processing of heavy crude, because heavy crude will be having more sulfur, metals, asphaltenes etc. So, in that case it will be creating more pollution and it will be creating other type of difficulty for the refinery also. So, what will be the technology that can be implemented for this process, that we are going to discuss in this class, and the contents are the heavy crude oil and its properties, then problems of heavy crude oil and its refinery solution, then conventional refining flow sheets and the need of oilhead processing, technologies for oilhead processing and advanced refinery configuration for processing heavy crude oil. Now, what is heavy crude oil? Already we have discussed in our previous class that when the API gravity is lower, then the crude oil becomes more heavier, and some example was light oil, medium heavy oil, heavy oil. These we have seen in the previous classes, and extra heavy oil and bitumen, these are also considered as heavy crude, that is bitumen can give us synthetic crude and extra heavy oil is also heavy crude. So, both conventional as unconventional type of crude sources are there. So, we can get synthetic crude oil even from these sources like tar sand and your bitumen and oil shale. So, we can get crude oil from this and that can be processed. So, how we can do it, that we are going to discuss. So, unconventional oils from enhanced oil recovery or tar sands and shale oils also considered as crude oil and synthetic crude are obtained from bitumen and that is tar sands and shale oils. So, synthetic crude is the output from a bitumen or extra heavy oil upgrader facility used in connection with oil sand production, and it may also refer to the shale oil and output from an oil shale pyrolysis. So, oil shale pyrolysis, shale oil is nothing but a rock, sedimentary rock which contains oil or the crude like material. So, that crude is produced from the shale oil through pyrolysis and that is synthetic crude. Similarly, synthetic crude can also be produced from bitumen or say tar sand. So, that is called extra heavy oil upgrader facility, they are producing this one. Now, if we compare the composition of this, say bitumen, heavy crude oil and syn crude oil. So, these are our matter of concerns, we are going to discuss on these, how this can be converted into clean fuels, and then these if we see the asphaltenes is here, heavy crude oil and bitumen both are having, but synthetic crude is not having that asphaltene. Then resins are there and then aromatics and saturates. So, saturates are increased, aromatics are increased in case of syn crude with respect to bitumen and heavy crude. Then syn crude, synthetic crude is produced that can be refined further. So, how we can get the synthetic crude? So, there are number of methods, and how we will refine this heavy crude? We are talking about the heavy crude, then the conventionally the heavy crude is transported to the refinery and then heavy crude is blended. The heavy crude is diluted with the addition of some diluent So, diluent addition, viscosity reductions. So, pumping cost reduced and it is transported through the pipeline to the refinery. Then once it is coming to refinery, then refinery operation starts and then it gives transfer fuels, high value products, and then the bottom part we get your asphaltenes here, and we can get also fuel oil or coke, already the similar conventional refinery configuration. That way it is followed. But the difficulty is that this heavy oil, it is having high viscous, highly viscous, it is high tan and high sulfur content, and pipeline transportation is also difficult and not comparable with a conventional refinery. So, this is not compatible with the conventional refinery. So, the important problems for this crude oil is that high crude side pressure drop. So, once we are pumping the heavy crude after diluent addition, then also its viscosity is higher than the light crude and it requires high pressure. So, when it is coming to the refinery side, the pressure drop takes place. So, this high pressure drop is required, and then the first step in the refinery is your desalting. So, desalting will also be difficult here because it contains more asphaltenes, more sulfur, etc. So, desalter upsets and poor desalting capacity performance we get here, and then rapid crude column condenser corrosion. So, when it is going for distillation, then the crude column will be having more corrosion, the condenser part will experience more corrosion. So, low diesel product yield, this feedstock will give low diesel product, and vacuum heater coking, vacuum column fouling. So, it can also make more fouling of this scale formation etc. take place, and high vacuum in vacuum distillation column we have to produce more vacuum, so that the more relatively heavier components will also come into the liquid form. So, lower high HVGO product, heavy vacuum gas oil product, this draw temperature and lower yield, and then high metals in feed to catalyst feed hydrotreater. We have high metal content. So, the feed, the liquid which will be generated, that can be sent for catalytic hydrocracking unit, that will be containing more metal. So, we have to need some demetallization unit for processing this, and general corrosion problems is higher in this case. So, these are major drawback or problems with the processing of heavy crude in a refinery. And for processing heavy crude oils or blends, these are the challenges: higher heater temperature. So, we need to put higher heater temperatures because already available materials in the feedstock is of high molecular weight. So, we need more temperature for its distillation, and lower atmospheric and vacuum column operating pressure. So, as we have already discussed, the lower the pressure we will get more hydrocarbons, high molecular hydrocarbons in liquid phase, and lower atmospheric column overflush, obviously overflush will be less because lighters are not there, are very less there. So, improved wash selection efficiency, and then better ATB VTB, atmospheric tower bottom, vacuum tower bottom stripping are needed to maintain product yield and quality. So, these are the basic features of the heavy crude oil processing. Now, we will see the prerequisite, what are the options or what we can do for the processing of this crude, this type of crude. So, there are some prerequisites. If tan is very high, acid number is very high, then some prerequisites as mentioned here, and if it is high metals, high pour point and high nitrogen content crude, then also we have some prerequisite. So, for the first case, say when the tan is very high, total acid number is high, so in that case we need to crude blending, but if the tan is 0.6 or less, then no modification is needed, otherwise there should be some blending options and that can be processed. And then pre-processing, if tan is there, so acid is there, so you have to neutralize it first before sending to the refinery. So, neutralization by alkali, this step is required, and then chemical addition. So, we may add some chemical to reduce the corrosive nature of the feedstock, and we need proper metallurgy also, because it is having high acid. So, I have to select more corrosion resistant materials, and one example is SS 317. So, SS 316 is considered as superior grade steel, and 317 is further is having more resistance to the corrosion than 316. So, that way we can use the SS 317, and for high pore, high metal and high nitrogen content crude, we can we may require a jetty for uploading. If it is a say high pour point and crude tanks to be heated, we have to put the crude tank heated so that it can be in liquid form. And then high metals, if high metals is present, then we have to demetallization catalyst for VGO processing, and crude blending is another option. So, the metal concentration will be reduced, and high nitrogen concentration crude if it is, then we have to add some demetallization, denitrogenation catalyst for VGO processing, and crude blending is also another option. So, these are the prerequisites to process the heavy crude having these high TAN, high pore, high metals and high nitrogen. Now, we will see the conventional refining flow sheet for heavy crude oil. So, if we have heavy crude oil, so that can go for distillation, that will give some amount of gas, that will give some amount of distillates, and most of will be residue. So, this residue or direct heavy crude oil, it can go through different processes like say carbon rejection process and hydrogen addition process. So, hydrogen addition process or carbon rejection process, this process will be followed first in the first step or the primary step. Then the product which you are getting, that will go for secondary step conversion, that is nothing but hydroprocessing. So, first will be primary processing, then secondary processing, though it will be the hydrogen addition or maybe carbon rejection, and then the second is hydroprocessing. Then ultimately we will get the products. There may be some commercial products, here some steps may be required for to fine tune the quality of the products. So, here for hydrogen addition processes, number of processes have been reported, like say hydro treating, hydro cracking, and here some fuel cracking is also there, only thermal treatment, and then coking. So, hydro treating may be of different technology, RDS, residual desulfurization, and then vacuum residue desulfurization. High valve is developed by Francis Asval group, this is one hydro treating process, and OCR is on stream catalyst replacement process, in this case hydrogen addition takes place, and hydro cracking is HOL, LC fining, HyCon and ABC. HyCon is a cell technology, so ABC technology. So, these are the technology licensors for hydro cracking, and fluid cracking, fluid catalytic cracking can also be used for this conversion, and then the carbon rejection, say delayed coking, fluid coking, flexi coking, already we have discussed about delayed coking. So, this coking can also take place for the conversions of this heavy crude to liquid part, and then to further hydroprocessing to get the commercial fuel, and we can get hydro visbreaking, or we can get solvent deasphalting. So, solvent deasphalting, DAO, deasphalted oil, then again hydroprocessing and commercial fuels, and asphaltins we can separate from this SDA unit, which can be used for other applications like road making, etc. So, this is the conventional refining flow sheet with heavy crude oil, and from this basis we can summarize that heavy crude oil is transported to refinery conventionally from the production field and then require high pumping cost. Desalting is not so easy at the refinery site, and fractional distillation produces different liquid products, gas and residues. The produced liquid products and residues undergo primary and secondary conversion reactions, and then primary conversion includes cracking, hydrotreating, solvent deasphalting, base breaking, coking, etc., and secondary processing includes hydroprocessing. So, this is about our conventional technology. Now, what are the difficulty with these conventional processes? Say we need to add some diluent, we are adding some diluent, then again diluent recovery is a question. It affects the economy of the process. So, supply concerns, where from we will get the diluent and what type of diluents we will add and how we will recover it from it. Okay. Then high pumping cost and expensive regeneration and recycle of the diluent. So, these are the difficulty with the diluent part, and then heated pipelines. So, we are using diluent, but if the temperature, ambient temperature changes through the path of the pipeline, then again it can be the flow can be ceased. So, we have to maintain the pipeline heated throughout the distance. So, high capital and operating cost is needed and low reliability. We do not know whether it will work, or it may be affected by some external agency factors, or maybe some fault at any time. So, it is not so reliable solution, the reliability is less, and very high viscosity, it is very high viscosity. So, shipping problems it will arise, and high metals I have already discussed, the refining problems will be there, and high CCR again refining problems, and high carbon need expensive hydrogenation. That hydrogenation unit is very essential for this, and this hydrogenation in the refinery, this is the expensive part of any refinery. So, that is why the difficulty with the crude, heavy crude operation at the refinery site is limited by these factors, is also restricted by these factors. So, people tried to get some preliminary removal of the impurities at the production site. So, oil head processing of heavy crude oil can reduce the transportation and refining cost. So, oil head processing is implemented. So, for that purpose, for oil head processing, what are the technology available? We have discussed some of those here, that is heavy oil upgrading technology, HTL, and then improved delayed coking unit, IDCU, and then cell upgrader technology, and GHUR upgrading process, that is gen oil hydroconversion upgrader, and solvent extractions, ROSE TM. Already we have discussed about the solvent deasphalting process, the same process, that is ROSE TM can be used, the solvent recovery can be done at supercritical condition. Now, we will see HTL TM process. So, this HTL TM process, this is developed by Ivanhoe Energy Incorporation. This is the proprietary heavy oil to light oil technology, and is designed to cost effectively process heavy oil in the field and produce a stable, significantly upgraded synthetic oil product. So, tar sand can also be used to convert synthetic crude through this route, and the energy is recovered. The byproduct energy can be used to generate steam or electricity. So, this is the flow sheet. So, in this case, this is the main reactor where sand is used. So, heated sand comes in contact with the crude and then cracks the hydrocarbons, and then lighter parts goes there. So, this is the rapid thermal processing methods. So, this RTP, rapid thermal processing reactor. So, in this case the process is based on a recirculating transport bed of hot sand to heat the heavy feedstock and convert them to lighter products. Then the upgraded products and the sand are separated in a cyclone. This is the cyclone, it is separated, upgraded products and sand is separated here. So, upgraded products is going there and then it is again recycled back. So, this is the process it is going on, and here we are getting the synthetic crude, then cyclone, and the products are quenched and routed to the atmospheric distillation unit. So, here it is going to this and this atmospheric distillation unit, and we get some feed, we can get the product. This feed from the bottom we can send here and then it is going there. So, some heat recovery can take place here also. So, HTLTM upgrading technology is a unique thermal cracking technology. So, in this case what is happening, the heaviest molecules which are present here, those are being cracked, lighter one is not being cracked, lighter is not cracked, it is going there. So, heavier is basically cracked. So, in the selective thermal cracking process, and then upgraded products does not require diluents or blending agents to move to the product through a pipeline. So, now synthetic crude we are getting, which is having lower viscosity than the feedstock, and it does not need any diluent. That is one great advantage for well site processing of the heavy crude, and the byproduct energy is also can be recovered, and this technology HTLTM technology that can be used in small scale is appropriate to grow field sited upgrading capacity along with resource development. So, minimum scale of this 10,000 to 15,000 barrel per day, and integrated HTL heavy oil production processing reduces liquid, solid and gaseous waste and emissions. Next we will say the improved delayed coking unit. So, this improved delayed coking unit, already we have discussed about the delayed coking unit. So, similar delayed coking unit will be used here, but that will be having some specific nature and it is improved than the conventional delayed coking unit. So, in the conventional delayed coking unit we had 16 to 18 hours of cycle time, but in this case it is reduced to 6 hours. So, it is more efficient than that one, and this IDCU has revolutionized delayed coker by eliminating in situ decooking process, that is why the time has been reduced, means it is continuous type operations in situ delayed cooking. So, 4 hours time for its coke removal is not necessary. So, can upgrade low API crude at the wellhead, tar sands, bitumen, heavy oil and other heavy feedstock can be processed by this process, and this improves the coker efficiency, profitability, reliability and safety, and significant improvement in quality and volume of liquid products by this process, and handles virtually any pumpable hydrocarbon feed and reduces coke yield. By this it reduces coke yield and significant heat recovery from steam production. Now, we will see the flow sheet for IDCU process. So, here we are having oil head, so here the oil we are getting. So, then we are adding steam and heating, then flash drum. The flash drum will give us some light crude and then it is going to coke drum, we are getting heater and then going for coke drum. Then coke drum it is kept for some time and then vapors from it is fractionated and again we are getting light crude off gas and then we are getting light crude. So, our heavy oil, heavy crude here, tar sand, heavy crude here. So, here we are getting light crude. In case of here vacuum residue delayed coking unit, we had vacuum residue here and we got gas and liquid product as well as coke from this place, but here we are getting pitch, and we are getting the liquid part here which is the light crude. So, this light crude will be transported to the refinery for further processing. Next, cell upgrader technology. Cell upgrader technology, this technology is developed by Shell. We will discuss this one. Before that, you see here this IDCU, this is, and the previous one also, this is on carbon rejection method, application of thermal method, no hydrogen is added here, but here this your cell upgrader technology we see this processes crude bitumen from oil sands into synthetic crude oil. So, it is also produces synthetic crude oil from the bitumen and extra heavy crude oil. So, this is based on hydrogenation. So, hydrogenation takes place here. So, hydrogen is added to convert the bitumen from Shell's Muskeg River mine in the Athabasca oil sands into refinery ready sweet or light crude oil. So, this is different from that of improved delayed coking unit. This process is based on hydrogenation and the previous one is based on carbon rejection routes. And this cell upgrader technology has a rated processing capacity of 2,55,000 barrels per day or 40,500 meter cube per day. So, this is the capacity, and in this case as we are using the tar sands. So, the impurities removal is needed. So, here Shell's enhanced froth treatment technology is used to remove the sand, clay, fine clay and water from oil sands froth to make clean bitumen suitable for upgrading via these hydrogenation methods. If we have more impurities and hydrogen if we added, then more hydrogen requirement will be there and the process will be less economic. So, those are removed first by cleaned by this Shell's enhanced froth treatment technology, and it produces lower levels of sulfur dioxide emissions than the alternative coking, because already it is removed, the sulfur is removed through the Shell's enhanced froth treatment technology. So, these are the basic features of the cell upgrader technology. Now, GHUR upgrading process. So, genuine hydroconversion process, this is also based on hydroconversion and then hydrogen addition methods. So, genuine hydroconversion upgrader is a flexible hydroconversion process, its conversion and hydrogenation is one stage, and then applicable for sour, acidic, heavy crude and heavy refinery feedstocks. This can be flexible, any feedstocks can be handled here, and then proprietary devices to mix the hydrogen and the hydrocarbon stream. So, hydrogen and hydrocarbon stream is mixed in the proprietary device, and supersaturation of hydrocarbon with hydrogen. Supersaturation takes place, high amount of hydrogen is sent and high conversion of feed under moderate operating conditions, and then stable products at high conversion level. So, they have claimed that at high conversion level it can give our stable products, and premium quality sweet synthetic crude can be achieved through this route, because hydrogen addition is taking place. So, removes the need for expensive diluent blending, again there is no need of diluent addition and then pumping. So, reducing this and flexibility of operation, and upgrader is economical at 10,000 BPD capacity. So, even at lower capacity relatively it can be economically used and operating cost is lower than the existing process. These are the claimed by these Genual as available in this website. And if we see the basic features of this GHU upgrading process, then we see that this Genual GHUR can be utilized to upgrade high sulfur, acidic, heavy crude, bitumen and refinery residue streams through the hydroprocessing to produce naphtha, kerosene, diesel and vacuum gas oil. This process scheme is based on fixed bed reactor and reactors are in sequence, So, different types of reaction takes place in sequence. So, this is a fixed bed reactor system. So, first reactor, it is a guard bed HDM hydro demetallization catalyst is remain in the first reactor. So, hydro demetallization. So, demetallization takes place first. Then second reactor with a highly active HDS, HDN and HYC catalyst, hydro desulfurization catalyst, hydro denitrogenation catalyst and hydro cracking catalyst. So, these catalysts are there in this reactor. And then unconverted residue which is not being converted, the residue sent to synthesis gas unit for H2 recovery, and then leftover gases are used for IGCC application. Now, we will compare this GHU advanced delayed coking. So, GHU technology and advanced delayed cooking. So, this is a carbon rejection method, this is hydrogen addition method. If we think about the type of processes, then if we see the residue conversion, we can get here up to 90%, here 70 to 85%. If we temperature low, this is high, because hydrogen addition low temperature, coking is high temperature. Volume output, we get 100 to 104% hydrogen addition we are doing. So, volume addition may take place. Coke production, there is no coke production, but here we can get 20 to 25% coke production. Desulfurization is here in case of hydrogenation unit, but here I do not get any desulfurization. Hydrotreating process includes hydrotreating, it does not hydrotreating, it does not include hydrotreating, requires further hydrotreating. And this is equipment, fewer equipments are GHU, where more processing is needed in delayed cooking, and water usage 10 to 15% less than cooking or air cooled, and then natural gas usage, this is optional or not, here it is available. In some cases natural gas usage is there to heat the preheat the feedstock. So, that way this is taken from this reference. So, now what we are getting, the conventionally which is practiced, that heavy crude oil, then it is diluent addition and then transport to refinery and processing at refinery side, this is replaced now by the introduction of oil head processing, then synthetic crude or lighter crude, then it is coming to refinery for further processing. So, heavy oil we have, it is the processing is added here, oil head processing, then it is may be added with diluent or may not be added with diluent depending upon the quality produced in this step, and it is sent to the refinery, and as usual the operation is there, refining operation will be there. So, in that way we can able to remove the asphaltenes at the product side. So, the load or the excess burden to the refinery side is reduced, and the quality of the products is also reduced, and the creation of pollution is also reduced by this process. So, up to this in this class, thank you very much for your patience.